Okay, Assalamualaikum and good morning. We continue our lecture about boundary layer. So I just want to wrap up the previous lecture about this one. So we already learned about three major terms in boundary layer. One is called the boundary layer thickness. So the symbol is delta, and the definition is written as this one: a distance from the surface where the local velocity equal 99% of the free stream velocity, capital U. So from the definition here, we could write the mathematical expression as this one: delta is equal to y, because the delta is the distance in y axis from u equal to 0 until u equal to 99% of capital U. So I already discussed about this in previous lecture. So and then we already discussed about the displacement thickness. So the definition is the distance the surface would have to move in y direction to reduce the flow pacing by a volume equivalent to the real effect of the boundary layer. So the symbol is delta star. And why we need to do this? Because we need to do some calculation. So before we create our equation, we must make sure that the conservation of mass must be fulfilled. So and then we could determine the equation for delta star by using the idea of this one. So means that the mass before it's enter the flat plate must be equal to the total mass on the flat plate here. So because from the shape, rectangular shape, and this curve nature shape is not equal, so we add an imaginary thickness here. So the thickness is delta star. So we calculation is made by using the idea of mass. So and then if we do the calculation, so we equalize mass before it's entering the flat plate and the mass, total mass on the flat plate, we could comes out the idea of delta star or the displacement thickness as this one. So I hope you could remember the equation. Delta star is equal integration from 0 to delta 1 minus u over u dy. So and then here again I would like to remind you, so it is very important for you to differentiate the terms of small u and capital U. So in my handwriting, usually I will write U as this one, and I will write U with a bar on it like this one to differentiate the small u and the capital U. So and then we already discussed about the momentum thickness. So the idea, the symbol is theta. The definition is the distance by which a surface would have to be moved parallel to itself toward the reference plane in an inviscid fluid stream of velocity capital U to give the same total momentum as exists between the surface and the reference plane in a real fluid. So the idea of this one is, again, to make sure that our calculation is correct. So we must make sure that the conservation of momentum that occur on that process, on that phenomenon, will conserve. So and then if we calculate this one by using this idea, we just add another layer here. So and then the thickness is theta. And then the calculation is almost the same. We must calculate the total momentum before it's entering the flat plate, and then we need to calculate the total momentum on the flat plate. So and then if we do this, so I think I already show you this calculation in previous lecture. So we could get the momentum thickness equation is like this. So theta is equal integration u over u 1 minus u over u dy. So and then this is the example how to use that one. For example, if we have a question of delta star over delta, determine the delta star over delta and theta over delta for the velocity distribution of u over uy over delta. So this is the u over uy over delta, means that this is the the shape of the velocity profile on the flat plate. So for example, we have a flat plate like this one. So and then we have a velocity profile. So we know that this is the capital U and this velocity is small u. So from this equation, we could write u small u is equal y over delta times capital U. So this is actually the equation for each u velocity here. So and then if we need to calculate or we need to determine what is the value of delta star and theta, so we could, if for delta star, so we start with the equation, we substitute the value of u over u, and then we integrate from 0 to delta, then we could get delta star is equal to 1 over 2 delta. So this is the idea or the simple calculation of delta star and theta. And then if we want to calculate the theta here, so this is the equation. We substitute the value of u over u here. So and then we could calculate, we could determine that theta over delta is equal 1 over 6 as shown in this slide. So from this calculation, at least you could self-check your calculation. So the value here is actually must less than 1. So it must be positive, it cannot be negative. And then the power of this delta is equal to 1. So if, for example, you calculate theta is equal 5 over 2, 5 over 3 delta square, so means that it is something wrong in your calculation. So the delta must only by the power of 1, and the value here is must be less than 1. So this is actually to check whether the your calculation is correct or not. So and then I would like to show you another equation, because if you refer back to our previous lecture, the main objective of boundary layer is to calculate the drag force, the lift force, and also to calculate the shear stress, because the shear stress is the only parameter that we don't know to calculate our lift and drag force. So and then until now, so we only managed to calculate the value of delta star, and theta. So means now I would like to introduce you another equation to help us calculating the value of shear stress. So we call it as von Karman equation. So it was introduced by von Karman around these years by using the idea of conservation of momentum. So the idea is very simple. We know that the flow here will give us momentum. So however, after the flow flows, the fluid flows on the surface, so because of the no slip condition, because of the resistance here, so the velocity distribution occur, the velocity varies like this, and then we found that there is a momentum deficit here. So I mean the losses of momentum occur. So the simple reason is because there is a friction due to the shear stress. So means that we could relate the idea of momentum with the idea of shear stress. And then we need to calculate. So the idea is very simple. We found that the momentum in must be equal to the momentum out. And then to calculate the momentum, so this is the equation. So momentum is mass times volume. So this is volume, and then mass here can be calculated as rho AV. Okay, I'm sorry. So rho is equal to m over volume. So mass is equal to rho and volume. Okay, so rho and V. So okay, so this is the idea of mass that we have. Okay, so and then first we calculate the idea of deficit momentum. So deficit momentum occur at this region. So because this region, this shape, this area is not symmetry and also not a simple shape, so we start to calculate the deficit momentum from one piece like this, a small area of this one. So let's say because it is too small, so we could assume that this area is rectangular. So and then the thickness here can be determined as dy because it is a small portion from the y-axis. And then we have a molecule here moving with a u velocity. And then from the simple mathematics, we could assume that the length of this one can be written as capital U minus U because the total length here is assumed as capital U as shown in this one. So and then we manage mass here is rho and volume. So rho is maintained as rho and volume here means that the length times the height and times the width. So we could calculate as capital U minus U dy and b because the width here is b. Okay, you just imagine that we have a 3D shape like that one. So we could write as this one. So and then this is the mass, and then to calculate the momentum, so means that the mass must be multiplied with velocity. So here the velocity must be small u because the velocity, the molecule is moving by small u velocity. So please do not take capital U minus u as your velocity. That is the reduction of the velocity. So and then we have the deficit momentum. For example, we write a small d here is m times velocity. So we have rho u minus u b dy times u. So and then okay, so this is the deficit momentum for only one small area of this one. So and then if we calculate all the value of this one, we do the integral process. We integral it. So we integral of small d. So let's say it will become the total momentum deficit. So it will become capital D here, and then we integral of this term. So we take out the not related terms from the integral area. So we take out rho and b outside here, and then we have u minus u dy. And then von Karman proposed, so we multiply left and right terms with u. We multiply this one with capital U square over capital U square. So as you know, U square over U square will give us 1. So it will not change the value of the terms. So we have a U square here, and then we have this term like this one. And then if we solve this term, we could get this simplified terms. So and then this term is actually similar with the equation of theta. So then we could write as d is equal to rho b u square and theta. So and then to ease our calculation, so we differentiate the value of capital D here with dx. So we have d dx equal rho b u square d theta dx, and then we save it, we determine as equation number 2. So and then, so because in this equation we still have a lot of unknown parameter, so we try to determine the idea of deficit momentum here from the idea of friction. So previously, I think you already know that we could calculate the force is equal times dA, and the force here is referred to the friction force. So we could say that the momentum losses is actually related to the friction. So we could write as dd is equal to tau dA. So this is refer to the friction that occur at one small area. So because that's why we use the dA here. So and then the dA here is actually the area. So means that if we have a plate here in 3D version, in 3D shape, so and then we are focusing on the small area here. So this is the dA. So means the dA here is, so the length here is dx because it is very small in x-axis, and the length here is b. Okay, so I hope you understand why we use the idea of b here, because this area is actually at the same x coordinate. So means that the shear stress on this line is equal. So uh, we could take the whole length of b. So from here we could write, substitute the value of dA here by b times dx, and then we bring the dx to the left hand side. So we could write d over dx is equal to tau b. So now we already have two terms of deficit momentum. So what we could do here is we equalize equation 2 and 3. So we have d over dx, rho b u square d theta dx equal tau b. So and then we could cancel out the value of b here. So and then we could have the equation of tau is equal to rho u square d theta dx. So this is called the von Karman equation. So and then again, so here we have the value of tau, and then sometimes we have the value of delta. So means that here the value of theta. So means here you need to know how to calculate the value of theta by using the idea of theta is equal to integration u over u 1 minus u over u here. Okay. So and then because sometimes it gives us two unknown parameter, so we need to prepare another equation for the shear stress. So the most suitable equation is from the Newton's law of viscosity. So we use the tau is equal to mu du dy at y equal to 0. So why we need to use the condition of y equal to 0? Because the maximum shear stress occur at y equal to 0. That's the first one. And the second one is the velocity distribution. Okay, so the friction here is maximum at wall, at surface. So means that we need to take this condition as y equal to 0, and then because the friction occur on the surface here, that's why we use the condition of y equal to 0 here. Okay, this is the example, the usage of the idea of von Karman. Okay, for example, determine the boundary layer thickness and drag coefficient in laminar boundary layer that have polynomial velocity profile. So, polynomial velocity profile means the equation or the profile will has maximum square or the power of 2. So this is the equation. So later on, I will show you all the equation involved in this syllabus. Okay, let's say we have a polynomial velocity profile as u over u equal to y over delta minus y over delta square. So and then we list two equation of shear stress. One is von Karman, rho u square d theta dx, and another one is the Newton law of viscosity, mu du dy at y equal to 0. And then we need to know how to determine the value of theta. So this is the equation. So you need to substitute the value of u over u here, and then you could solve it. You could get it is equal to 2 over 15 delta. So what you need to do is, it's very simple. So we start with the von Karman equation. So we have tau equal to rho u square d theta dx, and then we substitute the value of theta here with a 2 over 15 delta. So and then in some textbook, or you could simplify the way you write this one as rho u square times 2 over 15 times d delta over dx. Okay, in some textbook they will write as this one. So means that you bring the delta here to the d x here, to the d here. Okay. So this is the equation from the von Karman. So we write as equation 1, and then we calculate again the value of shear stress by using the idea of Newton's law of viscosity. So we try to solve the idea of du dy at y equal to 0. We have u over u as this one, and then we could differentiate it du dy as this one, and then we substitute the value of y equal to 0, so it means that we put it 0 here, so we could get that du dy at y equal to 0, du dy at y equal to 0 is now equal to 2 capital U delta. So, and then we substitute these terms into this one. So means that the tau now become mu 2u over delta. Okay, please be careful about this calculation, because sometimes student only takes the value of shear stress tau is equal to u over delta. So that's not correct. Please make sure that you substitute the value of du dy at y equal to 0 in the equation to get the final terms. So this equation can be written as equation 2, and I think you know how to do this because we have a two value of shear stress here. So we equalize the equation. So and then we could get, okay, because we have d delta over dx here. So and then what we need to do is we bring the d delta to the right hand side, and then we bring all the terms to the right hand side and except the terms of delta. So we have a delta here. So we have a delta times d delta is equal of this one. And then if we simplify this one, we could get it is 15 mu over rho u dx. So we have a d delta at the left and dx at the right. So and then we integrate both sides to get the full terms. So we integrate both sides. So we integrate it here. So we have a delta square over 2, and we have 15 mu over rho ux plus c. This is the constants. So we need to determine the value of constant. So if we have a flat plate like this one, so we could say that at x equal to 0 here, at the beginning of the flat plate, the delta is equal to 0. So and then the c is equal to 0. So mean after we substitute the value of delta 0 and x 0, so the c is 0, then we could have the final equation as this one. So we have delta square is equal 30 mu x over rho u, and then we need to rearrange this equation. So we could have delta is equal 5.48 x over square root Reynolds. So please make sure that you could calculate until this answer, because normally for boundary layer, the equation is refer back to the Reynolds number. So we will have a square root Reynolds everywhere, okay, in the equation. Okay, so this is the delta star, this is the delta, the boundary layer thickness for velocity profile, for polynomial velocity profile. So how to calculate this one? It is very simple. So we have a flat plate here. So we assume that this is the x-axis. So if this is x equal to 0, so let's say this is x equal to 5, this is x equal to 7. So if, let's say, if you want to calculate what is the boundary layer thickness at this point at x equal to 5. So we just use the idea of Reynolds number is rho u x over mu. So we substitute the value of 5 here. So and then we substitute the x here with 5. Let's say 5 meter. Okay, so and then we could determine the value of delta here. So again, the delta here, it is the physical it has physical thickness. So mean that delta is actually can be proved in experimental works. However, for delta star and theta, it is just an imaginary thickness. So means that the theta star the delta star and theta cannot be proved in experimental work. So the delta can be proved because it is a physical phenomenon. It is a real thickness. Okay, so and then if you want to calculate the thickness here, again, you just substitute the value of x in Reynolds number as 7 and this x as 7, and then you will get the value of delta here. So this is delta 1, this is delta 2 maybe, and the unit of delta is meter. Okay. So, but sometimes people will use millimeter because the thickness is very small. Okay. So this is the idea how to get the boundary layer thickness from the velocity profile. So and then if we continue our calculation here, so we could calculate the shear stress. Okay, shear stress, I advise you to take the shear stress from the Newton's law of viscosity, because you have tau for von Karman, you have tau rho u square d theta dx. Okay, the value here is not complete because it still have the differential form here d theta dx, so means you cannot calculate. So if you still want to use this, so you need to do tau dx is equal to rho u square d theta. You need to integrate both sides and so on and so forth, so then you will get the value of delta. So it will take time. So I just advise you to use the shear stress from the Newton's law of viscosity, because in this equation there are no differential terms. So means it already becomes equation. So we substitute the value of delta from our previous calculation. So we get the value of tau here. So it is 0.365 mu u over x and square root Reynolds number. And then we could calculate the local drag coefficient. So we have a two coefficient actually here. So we have the drag coefficient CD, and we have a local drag coefficient C with small d. So what is the difference between these? So the word local here is referred to one specific point. So the C and small d here is actually, if you have a flat plate here, so it will refer to one point here. So the coefficient for that area. Okay. However, for C and capital D, so it refers the average or the overall drag coefficient for that object. Okay, so and then to calculate the CD, so we are using the idea of this one. So we have tau is equal to CD 1 over 2 rho and u square. Okay, please be careful because I think you already know the drag force FD is equal to CD 1 over 2 rho AU square. Okay, so and then force here can be substitute with tau and A. So and then we cancel out the value of A, so mean we have the tau is equal 1 over 2 rho u square. That's why the equation here we not include the value of A. And then to differentiate between the local and the total, the average value of drag coefficient, so we just change the capital D here with a small d. So this is just to differentiate the terms. Okay, but the most important things is please do not include the area, the A in this equation. You must understand how the equation being developed. So we have the C small d here as 0.73 over square root Reynolds number. And then we could calculate the drag force. So the drag force is, the idea is simple. So we have a plate, so we have a shear stress on this small area, local area, and then we need to calculate the total shear stress here, okay, by using the idea of shear stress times A. So the area here can be written as B mean the width of this one from here to here and the total length of x. So that's why we start our calculation by using that one. So FD is the integration of tau B dx because it is integration of tau and dA. So and then the limit is from 0 to L. So this is the common terms in the boundary layer. So we assume that the capital L is the maximum length of the plate. So and then we substitute the value of shear stress here. So we have this term, and then we only want to integrate to dx. So mean we could separate the non-x term outside the integral terms. So however, please make sure that you really understand that Reynolds number here consists of x. So Reynolds number is rho u x over mu. So means that we need to expand the Reynolds number here to this term, and then we start to integrate. So after we integrate, we could have this term. You could try this, and then we substitute the limit 0 to L, and finally we could have this term. And then to calculate the drag coefficient, so this is the common equation. So FD drag force is CD 1 over 2 rho AU square. And then we could rearrange like this one. So we could substitute the value of A is L times B. So mean L is the total length and B is the width. So we substitute, we could simplify, and finally we could get the CD is equal 1.46 over square root Reynolds. So means that if you have a flat plate like this one, and then you could determine that the velocity profile is polynomial, means by the power of 2. So you could calculate the total drag coefficient for this flat plate is equal to 1.46 over square root Reynolds. So the calculation is quite easy. So first you need to determine what is the length of this plate. So let's say x is equal to 3 meters. So we could calculate the value of Reynolds number by substituting the x equal 3 meters in the equation here. So then you could calculate the value of drag coefficient. So it's depend on you actually. Okay, it's depend on you. Sometimes people start to calculate, people want to determine the value of CD first, and then they will get the value of FD. Because if you get the value of CD, you could use this equation, then you could have the value of drag force. But sometimes you need to calculate the drag force here by using this idea, and then you could you calculate the CD at the end of your calculation. So it depends on the question, or in your research, sometimes it's depend on the way you conduct the evaluation, whether it is experimental or the simulation. So it depends on you. Both idea are correct. Okay, so this is the common velocity profile for laminar boundary layer. So we have u over u by the power of 1, so y over delta. So this is the polynomial, means the by the power of 2. So this is the by the power of 3, and this is by the power of 4. So and then this is the sinusoidal, u over u sine pi over 2 y over delta. So I hope you could try at home, try to get the value of delta, local drag coefficient, and total drag coefficient, the drag coefficient, by using this 5 velocity profile, because this is the very common or our representative, our syllabus for laminar boundary layer. So this is the answer for that, for all the value here. So and then if you realize when we do the von Karman, so we will take the condition of u is equal to capital U, if you still remember. So means that it is quite not fixed, not aligned with the definition of delta, that equal to y at u equal to 99% of capital U. So we not use the idea of 99%. Okay, it's still okay because maybe that 1% is can be ignored. That's what von Karman assumed. Okay, and then after this, we will take a look for the idea of Blasius exact solution, because Blasius, another researcher that give a lot of contribution in boundary layer, will show how to calculate the boundary layer thickness by using the idea of 99% of capital U, because it used the idea of 99% here, so it used the exact definition of boundary layer, so means that we call this solution later on as Blasius exact solution. So we continue our lecture on this one. So this is very simple. So maybe some of you has a question why we have a specific velocity profile for boundary layer. For example, if we have u over u, so why we only have y over delta? Why not we have 5y over delta? And then if, for example, for u over u, the polynomial, the quadratic, so we have 2y over delta plus y over delta square. So why not we have 3 and 7, for example, here. So actually the velocity profile here is derived from the boundary condition. So means that it is worth for you, it is advantage for you if you could remember all the velocity profile from the power of 1 until power of 4. So and then we have a sinusoidal, means the u over u with a sine pi over 2 y over delta. So this is also determined by using the boundary condition. So means that the value is fixed. So here in this slide, I will show you the very simple one, how to derive the second order polynomial of velocity profile. So let's say we have a boundary condition, a boundary layer like this one. So and then we have a velocity profile in the boundary layer. So and then because it is second order polynomial, so means that it has by the power of 2. So we write the general equation of u equal a plus by plus cy square. So and then because we have 3 unknown parameter here, so mean we need to prepare 3 boundary condition to create 3 equation, then we could determine that the 3 unknown parameter. So the first condition is at this point, and the second and the third condition is at the upper point there. So and then for point number 1, so the boundary is y equal to 0 at u equal to 0. We substitute into the equation, so we get a is equal to 0. So means that after this, so we could neglect the value of a because the value of a is equal to 0. Now the general velocity profile will become u equal by plus cy squared. So and then at point number 2, boundary condition at point number 2, we could write y equal to delta, u is equal to capital U. Then we substitute into this equation, so we have the equation number 2 here. So and then at another condition that we could derive for point number 2 is y equal to delta at du dy equal to 0. So what is the meaning of du dy equal to 0? Means there are no changes of velocity according to y axis. So and then because we need to use the idea of du dy, so we have u here, so we write as du dy as this one, and then we substitute du dy at y equal to delta based on this condition, so we will get this term. So and then we could get b is equal to negative 2c delta, and then we determine as equation number 3. So and then we substitute, we use equation number 2 and number 3. So we could have this one, and then we could get the capital U is equal to C delta square, and then we could get C is equal negative U over delta square. So and then we could manage to get the value of B here. So B is equal to U over delta. Now we get the value of C, and then we get the value of B, and then we could substitute into this equation. So and then we could simplify it as U over U equal to Y over delta minus Y over delta square. So this is the velocity profile that we use in a laminar boundary layer for second order polynomial. So means that the velocity profile that I give you in the table in the previous lecture is actually derived from the boundary condition. So means that the value, the expression, the equation for the velocity profile is fixed. So this is actually comes from the idea of Navier-Stokes or the idea from the differential form solution. So you may refer to the previous chapter to solve this one.